Hey everybody, this lecture covers section 4.8, that is Trigonometric Equations. So basically what we're going to do, we will be solving equations involving trig functions. So how do we do that? So basically what we're going to try to do is solve some equation like this. Sine of x is equal to the square root of 2 over 2. Okay? So in previous sections what we've had the value of x, like the sine of pi over 4. That would be equal to the square root of 2 over 2. So here we're going to go backwards. We're going to try to figure out those angles for which the sine is equal to the square root of 2 over 2. So if we consider the sine function, let's graph the sine function. Basic sine function here. We know it goes between -1 and 1. And we'll scale our axis like normal. 2 pi, pi over 2. 3 pi over 2, and -2 pi, negative pi over 2, -3 pi over 2. Okay. So recall sine starts at 0 and then moves up. Right, so follow our unit circle, moves up. Then back down, down, up. So we have one period of the sine function here. And again, that's going to continue on forever and ever because it's periodic. Likewise, reverse. We have another period of the sine function here. And of course, that would also continue forever and ever. All right? So basically what we're going to try to do is try to figure out the angles for which this function attains the value of the square root of 2 over 2. Now the square root of 2 over 2 is slightly less than 1. Let's say he's right about here. It's about 0.7 actually. So if we draw this horizontal line, we're basically looking to see where this red line, this horizontal line, at y equals root 2 over 2 is equal to the sine function. So you can see we have a solution here, and here, and here, and here, and then on all subsequent upper waves on the right-hand side. Likewise, in the reverse direction. All right, so how do we do that? Well, we know that we can just go really to the unit circle to figure this stuff out, right? So here we're looking for the angle for which the sine function is equal to the square root of 2 over 2. So if you look over here, the sine is the y-coordinate on these points around the unit circle. So the first time we get there after 0 is right here. So you can see the sine is the square root of 2 over 2 at the angle pi over 4 or 45 degrees, right? So one of our solutions here, that's our pi over 4. And then it happens again, not too far away, at what value? Well, let's go around and see where the y-coordinate square root of 2 over 2 again. Here we see this, we attain the value of the square root of 2 over 2 at 3 pi over 4 as well. 3 pi over 4. And then it happens again on a separate period over here. So again, it happens here at the pi over 4 angle after 2 pi. Well, let's think about it. How many pi over 4s are in 2 whole pi's? Well, that would be 8. 8 pi over 4 is the same thing as 2 pi over 4. So the next one we get would be at 9 pi over 4. Okay. And then again at 2 more pi's after that, so 11 pi over 4 also. So you can see that there are infinitely many solutions to this equation, right? We also have negative values over here. So this would happen at negative 1, 2, 3, 4, 5 pi over 4 and negative 7 pi over 4. Okay. And again, more solutions exist this way. Okay. So using the unit circle, sine of x equals root 2 over 2. If we kind of just use the unit circle, we see that the solutions happen at pi over 4 and 3 pi over 4. And then an equivalent solution happens after 1 whole revolution. That would be our 9 pi over 4. Right? If we add 8 pi over 4, that would be 9 pi over 4. Here, if we add 2 pi, we'll get 11 pi over 4, and so on and so forth, right? So we have solutions like pi over 4 plus 2 pi, right? So any multiple of 2 pi is going to get us back to this location on the unit circle. So we just add 2 pi times n, right? So this accounts for all the solutions, pi over 4 in every revolution around or the reverse direction, right? And x will equal 3 pi over 4 plus 2 pi times n as well, right? So for here, another solution occurs 2 pi units away after 1 whole revolution, okay? So this is the basis of what we're trying to do here. So let's look at another example. So here's an example. Find all solutions to the trigonometric equations. Let's start out with the not so bad one. How about the cosine of x is equal to 1/2? Okay. So again, we're going to traverse the unit circle, trying to find out where the cosine is 1/2, and x will represent the angle at which that happens. So let's go over here to your unit circle. Remember, the cosine would be the x-coordinate of these points. So here, the sine is 1/2, so we don't want that one. Cosine is 1/2. First time we see it after 0 is right here. So one of our solutions is at pi over 3. So I'm going to draw just a generic unit circle here and mark my location. Pi over 3 is right there. And then where do we see it happen again? Well, that would be negative 1/2, so we don't want that. Negative 1/2 here, we don't want that. Positive 1/2 is what we're looking for. So the next time the cosine is 1/2 is at 5 pi over 3. That's in the 4th quadrant down here. 5 pi over 3. Okay. And nowhere else does that occur again, right? After 1 revolution. So we would have another revolution to get here, so it would add 2 pi. So it adds 6 pi over 3. That's equivalent to 2 pi. So that would be at 7 pi over 3. Adding 6 pi over 3 here would give us 11 pi over 3, and so on and so forth, around and around and around the unit circle. So here our solutions are x equals pi over 3 plus any coterminal angle with that. So to get back to that angle, we add 2 pi times some constant multiple. Again, n is some number, -1, 0, 1, ... Okay? And x equals 5 pi over 3 plus 2 pi times n. So here we have our solution, and we add 2 pi to get back to a coterminal angle, any multiple. So if n is 2, we would go around twice, we'd get back to that solution. Okay? All right, how about this one? Sine x equals cosine x. So here we're looking to see where the sine function is equal to the cosine function, right? So if we look around the unit circle, are there any points where the sine and cosine are equivalent to each other? Well, yes, right here, right? Right here we see the sine and cosine are equivalent, right? So we have found our solution at pi over 4. And where does that happen again? So if we go around, we have, well, is that true here? Are these two the same value? Are they equal? Well, no, because one's negative, right? One's negative, one's positive, so that's not a good angle. Go around here, we see they're both negative root 2 over 2 and negative root 2 over 2. So another solution happens at just the opposite side. That would be 5 pi over 4. Okay. So you can see here that if we are at pi over 4, we can go around 2 pi to get back to a solution. But we don't necessarily have to add 2 pi, right? In fact, we only have to go half a turn around the unit circle to get to our solutions. So we can actually write this solution in a more compact way. So x would equal pi over 4 plus, now how much do we have to add to get to here? It's a 180 degrees, right? Which corresponds to pi. So if we add any multiple of pi, then we're back to a solution. So we don't necessarily have to write them separately. Okay? C, let's look for when tangent of x equals the square root of 3. Okay. So this one's a little tougher, right? Because tangent, we can't see the value of tangent on the unit circle, right? We can only see the values of sine and cosine. So this is where some of those trigonometric identities come into play that are fairly useful. Remember that the tangent of x is equivalent to sine x over cos x, right? So we can actually rewrite this as the sine of x over the cosine of x equal to the square root of 3. That's an equivalent equation to the one above it. So what we need to do is figure out what combinations of sine and cosine, when we divide them, give us the square root of 3 over 2. Okay? So we know we only have a few options, right? So is 0 divided by 1 equal to the square root of 3? No. Is the square root of 2 divided by the square root of 2 equal to the square root of 3? Well, no, that's 1. So it's got to happen at either of the pi over 6 or pi over 3 points, right? So let's try dividing the square root of 2 by this, the 1/2 divided by the square root of 3 over 2. So we're just going to test that here. Is 1/2 divided by the square root of 3 over 2 equivalent to the square root of 3? Well, let's look. So remember, we're dividing two fractions, so we can multiply them, but change the second to its reciprocal, which is 1 over the square root of 3. If we rationalize, we'll get root 3 over 3. So this is not the solution that we are looking for, right? Square root of 3 divided by 3 is not equivalent to the square root of 3. So let's switch them around. Let's see if we divide the square root of 3 over 2 divided by 1/2, do we get what we're looking for? Well, let's divide root 3 over 2 times our reciprocal, 2 over 1, which is the square root of 3. So that's what we're looking for. So we're looking for all the points along the unit circle such that the sine is the square root of 3 over 2 and the cosine is 1/2. Or some combination of them that will give us positive root 3. So let's look around. In the first quadrant, we can find that pretty quickly. Remember, sine is the y-coordinate. So the y-coordinate is root 3 over 2, and the x-coordinate is 1/2. So we can see that the first solution on our unit circle happens at pi over 3. Okay? because that is where the sine is root 3 over 2 and cosine is 1/2. So when we divide them, we'll get root 3 over 2. That'll give us a tangent of root 3. Okay? So where does it occur again? Well, if we go over here, we see the same kind of makeup at the 2 pi over 3. But what happens if we divide these two values? Root 3 over 2 divided by negative 1/2 would give us negative root 3. So we can't include that. Going around, of course, this is not going to work. That's not going to work. How about this one? Is negative root 3 over 2 divided by negative 1/2 equal to positive root 3? Yes, it is. So we have another solution at 4 pi over 3. Okay? If we continue to go around, here's another point like we had, but if we divide, we get the negative square root of 3. So that is not a solution. This, of course, is not going to divide to the square root of 3. So we have found all the solutions on the unit circle such that tangent of x is equal to the square root of 3. So to generate all the solutions, we can do a similar technique as what we did last time. If you notice, pi over 3 and 4 pi over 3 are 180 degrees apart. So all we need to do is revolve pi units every time to get back to a solution. So x, our solution, is equal to pi over 3 plus any pi revolution. So pi times n. Okay? And we're assuming n is some integer. Let's try a couple more with the more obscure trig functions. So here's d. Let's solve the secant of x equals the square root of 2. Okay? So again, when we face something like this, the unit circle is not helpful at the moment because we can only see the sine and cosine of the angle. So what we need to do is utilize one of those trigonometric identities that we talked about previously. Remember that secant is related to cosine, right? Remember, secant equals 1 over cosine of x, or cosine is 1 over secant of x. So either of these identities can be helpful when we are solving this guy right here. Well, let's rewrite the secant in terms of cosine so that we can solve this guy. So we know that secant of x can be replaced by 1 over the cosine of x equals the square root of 2. Just like we did in the last example for tangent, we try to get things in terms of cosine or sine so that we can utilize this unit circle. So right now we are a little bit at a loss because we have the cosine downstairs here. But let's just do a little bit of algebra to rearrange this equation. So to cancel out this fraction, what we can do is multiply both sides by the cosine of x. Okay? So that's going to cancel out our cosines over here, leaving us with 1 equals the square root of 2 cosine of x. Of course, we want to solve this for cosine, so let's divide by the square root of 2 on both sides. These will cancel. So we get cosine x over here is equal to 1 over the square root of 2. Now to help out one more time, we can rationalize. So let's multiply by the square root of 2 over the square root of 2 on both sides. So on this side we get the square root of 2 over root 2 times root 2 is 2. That's equal to cosine of x. So now you can see we have an appropriate form for our trig function. We know there are some angles on the unit circle where cosine is root 2 over 2. So if we look, cosine is root 2 over 2 at pi over 4 and 7 pi over 4, right? So we have our unit circle again. At pi over 4 we have a solution, and at 7 pi over 4 we have a solution. Therefore, x is equal to, now we have to add 2 pi to get back to each, so we can separate this. It's pi over 4 plus 2 pi times n, and x equals 7 pi over 4 plus 2 pi times n. These are our solutions to this problem. Okay. So you can see that these simple trigonometric identities are very useful when we're solving these things. So if you're ever faced with a secant, cosecant, tangent, or cotangent, we try to utilize these identities to solve the equation. Okay? What happens if we have a more complex equation, let's say? Solve the trig equations. And we want to give our answer in degrees. Okay, so we want to find all of the solutions for the trig equations, but let's give our answers in degrees this time. Okay? So let's do this one. How about 2 sine x plus 1 equals 0. All right, so first things first, note that we can't really go to the unit circle at the moment because we have like 2 times the sine plus 1. So what we want to do is isolate the sine and hope that we get a special number on the right-hand side that exists on the unit circle as one of those coordinates. So first things first, we're going to solve this equation like we would for solving for x, right? So the first thing we're going to do is subtract 1 from both sides. These will cancel. So 2 sine x is equal to negative 1. And divide by 2 on both sides. Divide by 2, divide by 2. So we're concerned, these will cancel, concerned where sine of x is equal to negative 1/2. So again, we're looking for the angles for which this is true. So if we go to our unit circle, where is the sine equal to negative 1/2? Well, that would be negative 1/2 for the y value. So it's at this angle here and that angle there. Right? These are the angles that are closest to the axis, x-axis, so that would be right there at 7 pi over 6. And over here at 11 pi over 6. We want our angles actually in degrees, so that would be 210 degrees and 330 degrees. Okay. So you can see our solutions happen at 210 degrees plus every full revolution, so 360 degrees times n, and x equals 330 degrees plus 360 times n. Okay. Let's do one more in degrees. So b. Let's do 1 plus cotangent of x equals 0. So again, we want to isolate our trig function first, so we can subtract 1 from both sides. Cancel. So where is the cotangent of x equal to negative 1? So again, we want to utilize a trigonometric identity that we saw in the previous lectures to get our result. All right, so let's rewrite cotangent in terms of sine and cosine. Well, we know that tangent is sine divided by cosine, so cotangent is just the flip of that. Cosine divided by sine is negative 1. So let's figure out where cosine divided by sine is equal to negative 1. Well, we got to think a little bit. Well, how do we get a negative 1 when we divide two things? Well, those things have to be equal, but one of them has to be negative and one of them has to be positive, right? So we need to figure out where on the unit circle the cosine and sine are the same value, but one is positive and one is negative. Well, we can remember that that happens at the pi over 4s, right? The pi over 4 angles, we know we get a root 2 over 2, root 2 over 2 combination. So would we have a solution at pi over 4? Well, no, because both of them are positive. So when we divide, we'll get a positive 1. How about at 3 pi over 4? One is positive and one is negative, right? So at 3 pi over 4, we have a solution. And let's check our next pi over 4. Here they have the same sign, so we get a positive 1 on division. Here they have a different sign on division, different sign, so on division we would get a negative 1. So that's 7 pi over 4 as well. Of course, we want our answers in degrees, so that's 315 degrees or 135 degrees. Okay. So our solution would be, so here you can notice that we don't have to go around 2 pi to get to the next solution, but simply pi, right? Or 180 degrees. So we can say 135 degrees plus 180 degrees times n. And this accounts for all the solutions. All right, let's try some quadratic equations. So how do we do a quadratic equation in with these methods, okay? So let's consider cos squared of x minus 1 equals 0. Okay? So we want to solve the trig equations using radians for your answer. Okay? So here's a cos squared minus 1. So remember that with quadratic type equations, we can't do a solving process like this per se. What we would need to do is factor. So we would consider something. Looks like the basic quadratic y squared minus 1 equals 0, let's say, where y is just equal to the cosine of x, right? So here, how do we factor this? We would factor this using our difference of squares formula, right? That would be y plus 1 times y minus 1 equals 0. So the solutions would be y equal to negative 1 and y equal to positive 1. If we were doing this simple algebraic equation here. For our trigonometric equation, we can do the same thing. So notice that this is something squared minus something squared, right? So we're using the formula like a squared minus b squared. This will factor into a plus b times a minus b. It's our difference of squares formula. So what's our a? A is like cosine, right? Cosine squared, so a would be cosine. B squared is like 1, so b would be equal to 1. Therefore, we can factor this guy like cosine of x plus 1 times cosine of x minus 1 equals to 0. That means solutions occur where cosine of x equals negative 1 and cosine of x equals positive 1. So let's figure out where on the unit circle this happens and where on the unit circle that happens. So cosine is the x-coordinate. X-coordinate is positive 1 at 0, and it is negative 1 at pi, right? So our solutions happen here at 0 and here at pi. So let's try to write our solution using our more compact notation. Therefore, all the solutions happen at 0 plus n pi. Or just pi times n. Okay. Let's try another one. Let's try 2 sine squared x minus 3 sine x plus 1 equals 0. Alright, so this one is quadratic because it has that square term on it, and it reminds us of a algebraic equation like 2y squared minus 3y plus 1 equals 0. Right? It has that same look to it, except the y's are just signs. So how would I factor this? Well, we would have a binomial factor, right? So the first terms have to have a 2y and a y. And the last term has to be 1 and 1. The signs have to be the same here, but combined to give a negative, so both of them are negative. So you effectively factored the equation there. Right? If we were to check to see if we create this middle term, that we look at the outside and inside multiplications and then combine them. 2y times negative 1 is negative 2y. Negative 1 times y is negative 1y. Negative 2y and negative 1y make negative 3y. So this is the factored form of this equation. This is no different, right? We can actually, because this looks like this, the factors are going to look like this, except the y's will be signs. So we can rewrite this as 2 sine x minus 1 times sine x minus 1 equals 0. Okay. So this means that 2 sine x minus 1 equals 0 and sine x minus 1 equals 0. So we have two little equations to solve. Remember, this one is like one that we've done before. So we just solve this, find the solutions for this equation, solve this, find the solutions for that equation. So here we'll add 1 to both sides. 2 sine x equals 1. Divide by 2. Sine x equals 1/2. Here we just have to add 1, so sine x equals 1. So we need to figure out the angles in the unit circle for which these two things are true, right? So let's go for sine equal to 1. Where is the sine equal to 1? Well, where's the y-coordinate equal to 1 for these points? That happens right here, pi over 2. Okay. Does it happen anywhere else? Well, down here it would be negative 1. So we just have that one solution there. So the solutions that come from here are x equal to pi over 2 plus 2 pi n. It's one set of solutions. Now we need to look to see where sine x is equal to a half, because those are some more solutions. Sine is the y, and that's a half at pi over 6. And again at 5 pi over 6. And then any solutions down here will be negative because the y-coordinates are all negative down here in these two quadrants, right? So we do not consider any more solutions. All right, so let's write these out. Looks like we have to go all the way around to get to it. There's not one, it's not 180 degrees here. So the solutions from here are x equals pi over 6 plus 2 pi n, and x equals 5 pi over 6 plus 2 pi n. So we have three sets of solutions for this guy here. So again, with these quadratic equations, it is important to be able to factor them. Let's try one more of those. Let's see. Let's solve for cosine squared x minus 8 cosine x plus 3 equals 0. Alright, so this one kind of resembles the last one, so let's consider the basic function for y squared minus 8y plus 3 equals 0. So it's easier to kind of factor this out than having to deal with the cosines in here. So we just consider this to do our factorization. So let's see what we get. Alright, so we have some options for the first term, right? We could either do 4y and y, or 2y and 2y. The last numbers have to be 1 and 3. So let's choose 1 and 3 here. You know, the signs are the same, but combined to give us a negative, so negatives there. Let's try out 2y and 2i and see if that'll work for us. Okay, 2y and 2i. So let's see, if we multiply back the outer terms, that'll be negative 6y, and the inner terms are negative 2y combined to negative 8y. Good, that's what we're looking for, right? So those are the factors of that algebraic expression. So we can just copy that format over here, but use cosines instead of y's. So this factors into 2 cosine minus a half, minus 1, times 2 cosine minus 3 equals to 0. Alright, so let's look. So here we have 2 cosine x minus 1 equals 0. 2 cosine x minus 3 equals 0. And then solving this, we'll get 2 cosine equals 1, divide by 2, cosine equals a half. Solving here, we get 2 cosine x equals, add 3, so 3. And cosine x will equal 3 halves. Okay? So all we need to do is go around the unit circle and see where the cosine is a half and where it is 3 halves. Okay? So let's see. Cosine is the x, so where's cosine a half? Well, that happens here and there. So it looks like these are the pi over 3 angle and 5 pi over 3 angle. So the solutions generated from here are x equals pi over 3 plus 2 pi n, and x equals 5 pi over 3 plus 2 pi n. Okay. Now let's look, where's the cosine equal to 3 over 2? Well, we have spots where it's the square root of 3 over 2, right? So that's not what we're looking for. Do any of these points have 3 halves as their x-coordinate? It doesn't look like it, right? And why is that? Well, let's think about it. How big can the cosine get? The biggest number as an x-coordinate is 1, right? And what is root 3 over 2 is 1.5, right? So we know, if we kind of consider the graph of cosine, if I just draw a picture of it here, we know the highest it can possibly be is 1. Here's 1.5, so if we consider a horizontal line, that horizontal line is never going to hit the cosine function, right? It's because the highest cosine can ever get is positive 1, and the lowest it can ever get is negative 1, right? So any number that we're setting it equal to that's outside that range, we have no solution coming from that, right? No solution from this one, okay? So once again, 3 halves is too big. Remember, the cosine can only be a number between 1 and negative 1. Last up, we need to deal with, on occasion, there being a number inside with our x, okay? So how do we handle examples like this? Find all solutions for the equation in radians, let's say. So A, let's deal with cosine of 2x equals 1. So sometimes we have a number that's kind of hanging out on the inside with our x, all right? So with these ones, we consider the equation. So we want to consider just the cosine of y equal to 1. Right? So we consider cosine of y equal to 1. What are the solutions for this guy? Cosine is equal to 1 at one spot on the unit circle. That's at 0, right? At 0. So here y would equal 0 plus 2 pi n. Correct. Right? Y would equal 0 plus 2 pi n. So there's no difference here. So if the cosine of 2x is equal to 1, this means that 2x is equal to 0 plus 2 pi n. Zero plus 2 pi n. So we don't have our solution quite yet. We need to solve for x a little bit more. So we're going to divide both sides, or this is just 2x equals 2 pi n. So this means that 2 times our solution is equal to 2 pi n. So we divide both sides by 2. So our final answer is x equals, these 2's will cancel, pi n. So once again, we kind of disregard this, kind of just cover it up, ask ourselves, where's the cosine equal to 1? Well, that happens at 0 plus 2 pi n. So we set that inside bit equal to it, and then solve. Okay? Let's try another one like that. All right. Let's do sine 3 theta, or 3x, equals 1. Okay. So we do the same kind of thing with solving these guys, right? we want to isolate the trigonometric function. So we got to get rid of that 2 first by division. So divide both sides by 2. Cancel. So we get sine of 3x equals a half. So then again, we consider, kind of disregard that 3x for a minute. Where is the sine equal to a half on the unit circle? Well, sine is the y-coordinate, so that would be here, half, right? That's 1. So we have points there and there. So these aren't the pi over 4s, but these are the pi over 6 angles, right? The pi over 6 angle here is pi over 6. And over here, 5 pi over 6. Right. So the sine of 3x equals 1/2. Well, this angle, for what angles does it equal 1/2? These two, right? These two plus 2 pi n's. So we have 3x equals pi over 6 plus 2 pi n, and 3x equals 5 pi over 6 plus 2 pi n. So then all that's left to do is divide each side by 3, right? So we're going to divide here by 3, divide that by 3, divide that by 3. Divide this by 3, that by 3, that by 3. So here we get some cancellation, so that's going to be x equals. Now remember, when we divide by a number, we just multiply this denominator. So this would be pi over 18. Pi over 6 divided by 3 is pi over 18. Plus, now nothing's going to cancel here, so this is 2 pi over 3. So there's one set from our solution set. Here, divide, so we get x equals 5 pi over 6. Remember, so if we're dividing by a fraction by a whole number, we can think about multiplying by the reciprocal of that whole number, which is 1/3. So that's why we get that multiplication in the denominator. So here we get 5 pi over 18 plus, same thing, 2 pi over 3. So here are our solutions to that. All right, I think that does it for this lecture. You can go ahead and try the homework for this in WebAssign.